All right, guys, in this video we are going to finish out our discussion of hybrid orbitals and valence bond theory with a handful of practice problems. So to kick things off, let's do a quick recap of the method for determining the hybridization scheme for a given molecule. All right, so as you recall from the last lecture video, this is essentially a two-step process. The first step is to determine that electron geometry, and we're going to do this using valence shell electron repulsion theory, just as we did before. We're going to determine the number of electron groups around that central atom. And then, based on the number of electron groups that we need to accommodate, we will assign a hybridization scheme. And the table outlined in the following slide tells us what hybridization scheme is necessary based on the number of electron groups. So if you have two electron groups, we're going to need two of these hybrid orbitals. You're going to have an sp hybridization. Three electron groups, you're going to need three hybrid orbitals, so it'll be an sp2, total of three sp2 orbitals to account for that sort of arrangement. And of course, four electron groups, sp3, five electron groups, sp3d, total of five orbitals, and six electron groups, you'll need sp3d squared, right, d2. Okay. So it's really that straightforward. You find the Vesper, you find that electron geometry, and you use this table to determine that hybridization scheme. Okay, so let's go ahead and jump into our first example. So the first example here, we're looking at the compound acetaldehyde. And acetaldehyde here is a little bit more complicated, right? If we draw out that Lewis structure in our first step, we see that there are in fact really two carbons that we're going to be focusing in on that are going to have distinct geometries around them. We're going to have to determine distinct hybridizations for each one. Okay, and so we're going to have to really break this down into a two-step process. So let's first take a closer look at that carbon on the left-hand side. So the left-hand side carbon has, very clearly 1, 2, 3, 4 groups around, or 4 single bonds, 4 electron groups that we need to accommodate. Well, if you have 4 electron groups, then that's going to give you an sp3 hybridization, right, for that, to account for that tetrahedral geometry. So when we're drawing this out, right, we're going to put 4 of these sp3 orbitals. So we're denoting these sp3 orbitals here on the purple orbitals, following our coloring scheme on this left-hand carbon. So we'll do that. That'll be the starred carbon. Okay, and those sp3 orbitals are then interacting with a variety of different orbitals and forming the various bonds. We'll come through at the very end and add in all those bond types. Before we do that, let's jump over to this second carbon atom and take a closer look at the carbon atom here without the star on it. And of course, this carbon atom has that double bond to oxygen, and so it has a total of 3 different electron groups. 1 double bond to oxygen, a single bond to hydrogen, and then another single bond to the remaining carbon. Okay, so if you have an arrangement like this, then you're of course dealing with a trigonal planar geometry. So 3 electron groups, trigonal planar geometry, that's going to require an sp2 hybridization. So the orbitals here on this carbon atom on the left-hand side are actually sp2 hybrid orbitals. Okay, and once we've built up the hybrid orbitals on both of these carbons, we're now ready to go back and identify the specific types of bonds that are occurring based on the specific orbital overlappings. So the first carbon here, we'll go back to our starred carbon, has all these sp3 orbitals. Well, the first 3 bonds to hydrogen are simply going to be sigma bonds formed between the head-to-head overlap of carbon sp3 hybrid orbitals and the unhybridized 1s orbital on hydrogen. Right? Now, the fourth bond, right, the fourth hybrid orbital is actually going to be engaged in a head-on overlap with the sp2 hybrid orbital on carbon. And so this bond here, again, it is head-to-head overlap. So we are going to be looking at another sigma bond. But now it's a sigma bond between 2 carbon atoms, and even more specifically, it's a sigma bond formed between an sp3 orbital on the starred carbon atom on the left and the sp2 hybrid orbital on the carbon atom on the right. All right, and so then moving right along, we've got our hydrogen atom, another CH bond for that, CH bond coming off the carbonyl carbon here. We have a sigma bond formed between the carbon sp2 orbital and the 1s on hydrogen, and then a last sigma bond formed between the carbon and oxygen, where we have an sp2 on carbon overlapping with the unhybridized p on oxygen. Right? Now, keeping in mind that when we form that sp2 hybridization scheme, there is an unhybridized p orbital. This is denoted in red here in the diagram. That unhybridized p orbital has a single unpaired electron in it, which will then overlap with a similar unhybridized p orbital on oxygen with a single unpaired electron, giving rise to a side-to-side overlap, or a pi bond. So a pi bond then forms between the unhybridized p orbitals on carbon and oxygen. Okay, so hopefully you guys are seeing that it takes a while to kind of go through and label and identify all these bonds, but conceptually it's really not that much more challenging than identifying that electron geometry, right? You identify the electron geometry, we assign those hybrid orbitals, and then it's just walking through step by step and identifying each one of those bonds. All right, so the next example I want to look at is actually a little bit more basic molecule, but it's going to pave the way for kind of one of our final discussions here with hybridization. And this discussion is centered around the concept of a double bond. Okay, so let's step back for a second and then just make the Lewis dot structure for a very simple ethene molecule, C2H4, right? Lewis structure right here. Where basically we are going to follow through the scheme, and again, I encourage you guys to pause the video, make sure that you can build up this bonding arrangement. I don't expect the picture to be this nice. There's a reason why I use the textbook images for these guys. They're hard to draw, right? But hopefully you can understand where all these are coming from. You've got these trigonal planar carbons, all right, two of them, 2 carbons. So you're going to have sp2 orbitals on both carbon atoms, and you're going to then get sigma bonds to the hydrogens, a sigma bond between the carbons where you're going to have overlap between the two sp2 hybrids on the left and right hand carbon, and then of course we will have an unhybridized p orbital on both carbons, each with a single electron. They will overlap and you get your pi bonding. Okay, so I want you to keep in mind, look at this structure of the pi bond, right? The fact that we have this orbital, this p orbital side-to-side overlap that we call a pi bond, that basically places this electron density on the top and bottom of that plane of atoms, has some very important consequences. And these consequences are perhaps best illustrated through the concept of structural, or geometric in this case, isomerism. So a quick note here, definition. What do I mean by structural isomerism? Well, basically a structural isomer, or a pair of structural isomers I should say, are a set of two molecules with distinct bonding arrangements but the same molecular formula. Okay, so in the example I'm going to give you here, I'm going to take a dichloro 1,2 dichloroethane, right? Basically, we've got a 2 carbon group with the chlorines on one chlorine attached to each one of the carbons, and I want to compare this to this dichloroethene, where you have a double bond between the 2 carbons. And I want to use the same sort of bonding framework that we just laid out in the previous slide to highlight what the structure of this double bonded dichloroethene molecule looks like. Okay, so these pi bonds kind of on the bottom and on the top of the plane of these molecules. All right. Okay, so what happens here? If you look at the single bonded case, right, where we don't have that double bond, you get only a head-to-head overlap, between these 2 carbon atoms. And you can imagine that if we spin one of these carbon atom groups around relative to the other, the overlap essentially remains unchanged. It is cylindrically symmetric electron distribution. So if I draw an axis right through the bond there, but the carbon-carbon bond, right, that electron density is symmetric around that axis. So spinning around that axis does not actually affect the overall orbital overlap, and hence it doesn't change the bonding interaction, right? You maintain that single bond no matter what you do. Okay, now the situation is different here with the double bond. All right, so this double bond, it is dependent on the side-to-side overlap of these p orbitals. You must have two p orbitals that are lined up right like this and right like this on bottom. If you rotate one of those p orbitals relative to the other, right, you end up getting a situation like this. And a situation like this reduces the overlap of the orbitals. All right, and if you turn this all the way to 90 degrees, you can actually get this to a point where you're effectively breaking that double bond. Okay, you're breaking that pi bond, right? And so what ends up happening here is that when you introduce this double bond, you effectively constrain the geometry. If two atoms are on one side of the double bond, well, then they can't move. They can't change without breaking that double bond. You'd actually have to break the double bond in order to form a dichloroethene molecule that looks like this. Okay, and so this sort of constrained rotation has some pretty cool consequences. And my favorite example of this is actually in understanding the chemistry involved in vision. All right, so I don't know if you guys have ever wondered of how we can take just light from our surrounding environment and how that light from our surrounding environment impacts our retina and somehow gets translated into what we all come to take for granted as our visual perception, right? So this process actually all boils down to double bond chemistry, believe it or not. Okay, so effectively what's happening here in the chemistry of vision is that light comes into your retina, right? And it will impact a molecule. It's called retinal, right? So I have it drawn out here. This molecule, retinal, right? And this retinal molecule has has a number of double bonds, but one double bond that's of particular importance, okay? And this double bond can exist in one of two possible states. Okay, you can either have this long carbon group on the right hand side going up and the long carbon group on the other side going down the other way. These long carbon groups are effectively on opposite sides of the double bond. We call that a trans configuration, so we're going to call this transretinal. Now, if you break that double bond and rotate this group down, you get the two long carbon chains coming down on the same side with that double bond. And if the two groups are on the same side of the double bond, we call that a cis configuration. We're going to call the resulting molecule cis-retinal. Okay, now remember, in order to change between these two configurations, cis and trans-retinal, you need to actually break a pi bond. You need to break that overlap between the two p orbitals. Okay, and so that requires energy. And so in the context of vision, what ends up happening is light comes in, and that light comes in and hits your retina. It's actually absorbed. If it's of the correct frequency, it's absorbed by this retinal compound, and it will, if it's again of the correct frequency, have sufficient energy to break that pi bond. And breaking of that pi bond will then allow this transition from cis to trans. Okay, so light is literally causing this molecule to go from right down like this to something where it's kind of pointing up like this. Okay, so a structural change in the molecule occurs when light hits it. Okay, now this structural change in the molecule is then coupled to a structural change in the protein that's holding on to that molecule, right? And those, you guys will learn more about this as you're, take more courses in biology, but, cells, they're all comprised of, these lipid bilayers with embedded proteins in them, and these proteins are the little molecular machines that carry out all the functions of life, right? And so this little molecule is embedded in a protein. You flip that cis to trans, you change the configuration of that protein, which results in downstream signaling cascades being put forward that ultimately signal the brain, hey, you saw a photon. Okay, so here we have it. Double bond chemistry is really that foundation, for that chemistry of vision, and understanding this valence bond model really allows us to appreciate why this occurs, really at a deep quantum mechanical level, at the level of how these electrons actually look. Okay, so that rounds out our set of examples here. Again, every one of these guys really boil down to remembering these two tables, right? If you can remember this mapping, right, then you've got your Lewis dot structures down pat, then you're really in good shape. I encourage you now to go ahead and bring up those practice problems and test that knowledge.